Hey everyone, and welcome back for another deep dive. You ready to jump in?
Absolutely. I'm excited for this one.
Okay, cool. So today we're going to be looking at something
Yeah.
that you can't really see, but it's all around us.
Mm.
It's what powers a lot of our world.
Mm.
Alternating current, or AC.
Yeah.
We're going to try to understand how we can actually measure
Right.
this invisible force.
Okay.
And we're going to be pulling from all sorts of cool sources for this one. We've got some electronics textbooks, technical documents.
Sounds good.
And
That's good.
yeah, I think it's really fascinating that we can
Yeah.
learn so much about something we can't even see.
It's true. I mean, you flip a light switch and the light comes on,
Right.
but what's actually happening there? Like,
Yeah.
what is that?
Exactly.
Yeah.
Yeah. And we're going to be talking about all sorts of cool tools
Okay.
to measure it. We've got meters, oscilloscopes, and even something called a bode plotter.
That sounds fancy.
It does sound fancy. We'll get to that later.
Yeah.
So first off, I think it's important to just touch on what AC is.
Yeah.
And how it's different from direct current or DC.
Right.
I think a lot of people listening already know this, but it's
Yeah.
worth reiterating.
Yeah.
So how would you explain the difference between those two?
Well, DC's like a nice, steady stream of water. Like you said, it's direct.
Okay.
It's going one way.
Uh-huh.
Think about like a battery.
Yeah.
Very predictable, very consistent.
Right.
Whereas AC, it's like waves on the ocean.
Okay.
It's going up and down, constantly changing direction.
Right.
And that's why it's so good for transmitting power over long distances.
Interesting. So DC is kind of like that
Yeah.
that constant flow from your kitchen faucet,
Exactly.
and then AC is like the ocean waves.
Exactly.
Okay. So that's a good analogy to keep in mind, but it makes it sound really difficult to measure if it's constantly going back and forth like that.
Yeah, like how do we even get a handle on that?
Right. So where do we even begin with measuring AC?
Well, believe it or not, we can actually use the same type of meter that's used for measuring DC.
Really?
Yeah, the D'Arsonval meter or a moving coil meter.
Okay.
It can be adapted for AC measurement.
How do you do that?
The key is something called rectification.
Rectification. That sounds intense.
It sounds complicated, but it's actually a pretty simple concept. Essentially, it's like having a one-way valve for electricity. We use these things called diodes,
Okay.
and they ensure that the current can only flow in one direction. So basically what we're doing is taking those AC waves, those rising and falling tides,
Right.
and turning them into a pulsating DC signal.
Okay.
Then the meter can easily read that.
So we're kind of smoothing out.
Yeah, exactly.
Yeah,
Smoothing out those choppy waves to get a steady measurement.
Okay. Gotcha. So that's one way to measure AC.
Yes,
But I know there's also another type of meter called this iron vein meter movement.
that's right.
And that can measure AC directly, right?
Exactly. It doesn't need that conversion to DC.
So how does that work?
This one uses a really clever trick.
Okay.
You see, when the AC current flows through the meter, it creates a magnetic field.
Oh,
And this field interacts with a small iron vein inside the meter,
Okay.
causing it to move.
Interesting.
The more current that's flowing, the stronger the magnetic field and the more the vein moves.
Oh, so the AC current itself is basically moving the needle.
Exactly. It's pretty neat, huh?
That is really clever. But our sources mentioned that iron vein meters aren't as accurate as the rectified ones,
That's true. They're generally less accurate.
and they work best at lower frequencies.
Right. Like the 60 hertz we use in our power grids.
Okay, that makes sense.
Yeah.
Of course, we also have those digital multimeters
Yeah.
nowadays that can measure both AC and DC really well.
Those are super handy, much more versatile.
Yeah. But I think it's still interesting to know how those older meters work.
It is. It gives you a good foundation for understanding the principles behind it all.
Definitely. It's like peeking behind the curtain to see how it all works.
Yeah.
So speaking of clever ways to measure things,
Uh-huh.
our sources also talked about something called a clamp-on ammeter.
Oh, yeah, the clamp on.
It sounds pretty...
It does what it says on the tin.
Yeah, like you clamp it on and it measures.
Exactly.
But how does it actually measure the current?
Well, this one's all about magnetic fields, too.
Oh, okay.
It's like a detective using clues to solve a case.
Oh, okay.
So remember how the iron vein meter used the magnetic field created by the AC current?
Right.
Well, the clamp-on ammeter takes this idea a step further.
Okay. How so?
So imagine you've got a wire carrying a lot of current.
Okay.
Now that current creates a magnetic field around the wire.
Right.
The clamp-on ammeter has this special core
Yeah.
that can open up
Okay.
and close around the wire like a donut.
I'm picturing it
You got it. And when you clamp it on the magnetic field from the current in the wire, induces a voltage in a coil inside the meter.
Interesting.
So the stronger the current, the stronger the magnetic field, and the higher the induced voltage.
Okay.
The meter then takes that voltage and translates it into a current reading.
So it's kind of like a blood pressure cuff.
That's a great analogy.
Right. You're measuring the flow, but you're not actually interrupting anything.
Exactly. You're not cutting into the wire.
That's really clever.
Yeah.
Our sources also mentioned that this is good for measuring the high currents.
That's right. It's particularly useful for high currents.
Why is that?
Well, for lower currents, the magnetic field might be too weak to actually induce a measurable voltage.
So you need that strong current to...
Exactly. You need a strong signal to get a good reading.
Makes sense. That's why they're often used in like industrial settings.
Exactly. Places with heavy-duty currents.
Where you have those big power flows.
Yep. Power distribution systems, things like that.
Gotcha. So we've talked about a couple different types of meters, but let's say we want to get even more detail about our AC. We want to actually see the waves in action. And that's where the oscilloscope comes in, right?
The oscilloscope. Now that's where things get really interesting.
Yeah. Our sources describe it as almost like X-ray vision for electronics.
That's a good way to put it. It lets us visualize those AC waveforms.
So we can actually see those waves.
We can see them, their shape, their frequency, everything.
Rising and falling like ocean waves.
Exactly. Just like watching the tide come in and out.
Okay. But how does that actually work?
It's a pretty complex process.
Yeah.
But the basic idea is fascinating.
Okay.
At the heart of it all is a cathode ray tube, or CRT.
Okay.
It's like a mini TV screen with an electron gun that fires a beam of electrons at the screen.
Okay. So we're shooting electrons at a screen.
We are, to create the image.
That's pretty wild.
It is pretty wild. And the AC signal, the one we're measuring, gets amplified and used to control where that beam hits the sky.
So the AC signal is controlling...
Yes, it's directing the show.
Where those electrons go.
Exactly.
Okay.
But how?
Inside the CRT, there are these things called deflection plates.
Deflection plates?
Yeah. It's basically two pairs of metal plates that create electric fields.
Yeah.
One pair controls the up and down movement of the electron beam.
Okay.
And the other pair controls the left and right movement.
So they're kind of like magnets, pushing and pulling.
That's a great analogy.
The electrons.
Yeah, think of it that way. The voltage of the AC signal determines the strength of those electric fields.
Gotcha.
And remember, electrons are negatively charged.
Right.
So they're attracted to the positive plate
Ah.
and repelled by the negative plate.
Okay.
So as the voltage changes...
It changes the strength and direction of those fields.
Right.
Which causes the beam to move up and down, left and right.
So the AC signal is basically choreographing a dance.
It is. It's like a little electron ballet.
For that electron beam on the screen.
Exactly.
That's pretty amazing.
It is, and the result is that you see the AC waveform traced out on the screen.
Wow. That's really mind-blowing.
It is pretty cool.
That something so fundamental as like electrical attraction and repulsion can be used to create such a sophisticated tool.
It's a testament to human ingenuity, for sure.
Definitely. And that's just the beginning.
Right, we're just scratching the surface here.
Of how oscilloscopes work.
There's a lot more to explore.
Yeah. There's a lot more to unpack.
Yeah, we'll get into the sweep generator and triggering next time.
All right, sounds good.
That's where things get even more fascinating.
I can't wait. This is already making my head spin a little bit.
That's a lot to take in.
But in a good way. I'm definitely hooked.
Good, I'm glad.
I'm ready to learn more.
All right, we'll pick it up next time.
Perfect, thanks.
You got it.
All right, so we're back and ready to dive deeper into the world of oscilloscopes.
Yeah, those things are pretty amazing.
They really are. It's like we were saying before.
Yeah.
They give us this incredible ability to actually see those AC waveforms. It's like watching a tiny little electron ballet on the screen.
It's a good analogy.
Right. But we're only just starting to understand.
Right. We've just scratched the surface.
How they work. There's so much more to uncover.
There is.
You mentioned this thing called a sweep generator earlier.
Oh, yeah, the sweep generator.
What is that exactly? Is that like the choreographer of our electron ballet?
You could say that.
Okay.
That's what creates the time axis on the screen.
Okay, the time axis.
Yeah. It generates this special signal called a sawtooth wave.
A sawtooth wave, okay.
Yeah, and that's what makes the beam sweep across the screen.
I'm trying to picture this sawtooth wave.
All right, well, imagine a ramp that goes up at a steady pace and then drops suddenly back down.
Okay.
And then it repeats.
So it's constantly ramping up and then resetting.
Exactly.
Okay, I can see that.
And that sawtooth wave is sent to those horizontal deflection plates.
Right, the ones that control the left and right movement.
Exactly. So as that voltage ramps up, the electron beam moves smoothly across the screen.
Okay, from left to right.
Yep. And then when the voltage drops back down,
right,
the beam snaps back to the left side.
Okay, so it's like the sweep generator is setting the pace.
It is. It's the conductor of the orchestra.
For the electron beam.
Yeah.
Making it move across the screen in this predictable pattern.
Yes, a very precise and repeating pattern.
Okay, so that creates the time element on the display.
It does.
But then how do we make sure that the AC waveform we're measuring actually stays still on the screen?
Right, because if the beam is constantly sweeping...
Yeah, it seems like it would just be a blur.
That's a great point. That's where triggering comes in.
Triggering.
Yeah. Triggering is what synchronizes the sweep with the incoming AC signal.
So it's like telling the oscilloscope when to start sweeping.
Exactly. So it always captures the waveform in the same position.
Oh, okay. So it's like setting a starting line for a race.
Yeah, a good way to think about it.
Okay.
The oscilloscope has this trigger circuit that's looking for a specific event in the AC signal.
Like what kind of event?
Well, it could be when the voltage crosses a certain threshold or reaches a peak.
Okay.
And once it detects that event,
yeah,
it tells the sweep generator to go.
So it's like setting a trap.
Huh. Yeah, you could say that.
For the AC waveform, making sure we catch it
you got
at the same point in its cycle.
Exactly, and that way the waveform appears stationary on the screen.
Okay, even though the beam is still sweeping.
Right, even though it's constantly moving.
That's really clever.
It is. It's a brilliant solution.
It's like hitting pause on a high-speed camera.
Yeah.
At just the right moment.
A very precise pause button.
Okay, but there's one more thing I'm curious about.
All right, what's that?
Our sources mentioned that an oscilloscope needs to be calibrated.
Oh, yeah. Calibration is important.
What is that for?
Well, calibration is all about making sure the measurements are accurate.
Right, because you wouldn't want to use a ruler with uneven markings.
You need a reliable reference point.
Right. You need to know that your measurements are actually meaningful.
Absolutely.
So how do you calibrate an oscilloscope?
Most oscilloscopes have this built-in voltage calibrator that produces a really precise signal. And we use that to compare to the markings on the screen.
Right, the graticule.
That's right, the grid on the screen.
So it's like setting the ruler for the oscilloscope.
Exactly. You're making sure the vertical and horizontal scales are reading correctly.
So it's all about making sure those measurements of voltage and time
yes, it's all about
are accurate.
Precisely.
This is all starting to make a lot more sense now.
Good. I'm glad.
It's amazing how much thought and engineering
it's incredible
goes into making these tools work so reliably and accurately.
It's a testament to human ingenuity.
Definitely. I feel like we could do a whole deep dive.
We probably could.
Just on oscilloscopes.
Yeah, there's so much to explore there.
But for now, let's move on
to
another role that we talked about earlier.
All right, which one?
The frequency counter.
Ah, yes, the frequency counter.
It sounds like a pretty simple device.
It is, relatively speaking.
But I'm still curious about how it actually works.
Well, it's specifically designed to measure the frequency of an AC signal.
Right, how many cycles it completes per second.
Exactly, and despite sounding simple, the inner workings are pretty fascinating.
Okay, I'm ready to be fascinated.
All right, well, the first stage is the signal conditioner.
The signal conditioner?
Yeah. Think of it like a gatekeeper, preparing the signal for measurement.
So what kind of preparation does the signal need?
Well, it involves cleaning up the signal, removing any noise or distortion that could mess with the measurement.
So it's making sure the signal is nice and clean.
Exactly, getting it ready for its close-up.
Okay, gotcha. So the signal conditioner is like giving the AC waveform a little spa treatment.
Yeah, you could say that.
Getting it all prepped.
Making it presentable.
Okay. And then what happens?
All right. Well, once the signal is conditioned, it encounters the main gate.
The main gate.
Yeah. This gate is controlled by the gate control circuit.
Okay, the gate control circuit. That sounds important.
It is. It's responsible for synchronizing the counting process with the time base.
Okay, hold on. We're talking about a time base now and a gate. It's starting to...
Yeah, it gets a little complex.
Sound a bit like a science fiction movie.
It's all about timing, though. The frequency counter has this really accurate internal clock.
Okay.
That's the time base. And it determines how long that main gate stays open.
Okay. So imagine the gate is like a turnstile.
Okay. I like that.
That only lets people through for a very specific amount of time.
Exactly. And the gate control circuit is like the operator of that turnstile.
Making sure it opens and closes.
Yep. For a very precise duration.
At the right time.
Determined by the time base.
Gotcha. And during that open time,
right,
what's happening?
Well, that's when the pulses from the AC signal get to pass through the gate. And they get counted by the decade counter.
The decade counter. Yeah. So it's like the ticket taker at our turnstile.
Yeah, that's a good way to think about it.
Keeping track of how many pulses get through.
Counting each one.
During that specific time.
Exactly.
So what's so special about a decade counter?
Well, it's a digital circuit.
Okay.
That can count up to 10.
Up to 10?
Yeah. Think of it like an old-fashioned odometer.
Okay, like in a car?
Yeah, with those numbers flipping over.
Right.
So each time a pulse comes through, the counter increments its count. And when it reaches 10, it rolls over to 0.
Okay.
And sends a carry signal to the next counter in the chain.
So it's like a chain of these odometers.
Exactly. And each one represents a digit in the total count.
That's really clever.
Yeah.
So by chaining together multiple counters, you can count a huge number of pulses.
You can. You can measure a wide range of frequencies that way.
Okay. And it's all thanks to integrated circuits.
That's right.
That we can fit all of this counting power.
I know. It's pretty amazing.
Onto a tiny chip.
It's mind-blowing how much technology has advanced.
It really is.
Yeah.
It's incredible how something that seems so simple, like counting pulses, can be used to figure out something as fundamental as the frequency.
It is pretty remarkable.
From an AC signal.
It really speaks to the power of digital electronics.
It does. We've covered a lot of ground today.
We have, from oscilloscopes to frequency counters.
Yeah. Maybe it's time for a quick break.
Yeah, let's take a breather.
Before we move on to our last AC measurement tool.
All right, sounds good.
The Bode plotter.
Ah, yes, the Bode plotter. That's a special one.
I'm excited to learn more about that.
Okay, we'll dive into that after the break.
Sounds good. Okay, so we're back.
Back for more.
Ready to finish our deep dive into the world of AC measurement.
All right, let's do it.
We've learned about all sorts of tools.
Yeah? Meters, oscilloscopes?
Yeah, frequency counters.
It's been a journey.
It has. But there's one more device on our list.
Okay.
And it sounds like it might be the most specialized yet.
Oh, yeah. This one's pretty niche.
Okay.
It's the Bode plotter.
The Bode plotter.
Yep. It has a very specific purpose.
Okay. What's that?
It's all about analyzing a circuit's frequency response.
Frequency response? I'm not sure I'm familiar with that term.
Okay. Well, basically, every electronic circuit reacts differently to different frequencies.
Okay, so some frequencies pass through easily and others are blocked.
Exactly. Some might get amplified, some might get attenuated.
So it's kind of like how different musical instruments have different sounds.
That's a great analogy.
Right. A flute sounds different from a trumpet.
Yeah.
Because they're producing different frequencies.
Exactly. Different frequencies of sound waves.
Okay, so a circuit's frequency response is like its own unique sound.
Yeah, you could think of it that way.
It's like its musical fingerprint.
All
right, I like that. So the Bode plotter helps us map out that fingerprint.
It does. It sends a sweep of AC signals through the circuit.
It's covering a wide range of frequencies.
Yeah, to see how the circuit reacts to each one.
So it's like giving the circuit a hearing test.
Huh. That's a good way to put it.
Playing all these different tones?
Yep, and seeing which ones it likes best.
Okay. And what's it measuring?
It's measuring two main things.
Okay.
The gain and the phase shift.
Oh, right. We talked about those with oscilloscopes.
Yep. Remember, gain is how much the signal is amplified.
Or attenuated by the circuit.
That's right. And phase shift is like a time delay.
Okay. So how do those measurements help us understand?
Well, the Bode plotter takes those measurements and creates two graphs.
Two graphs.
One graph shows the gain versus frequency.
Okay, so that shows how much the signal is amplified.
Exactly.
By different frequency.
You got it. And the other graph shows the phase shift versus frequency.
So that shows any time delays the circuit might be introducing.
Exactly, at different frequencies.
Okay, so we're basically looking at two maps.
Yeah, two different perspectives.
One showing how the circuit affects the signal's strength.
Yep.
And the other showing how it affects the signal's timing.
You got it. And those are called Bode plots.
Bode plots.
Yep. And by analyzing those plots, engineers can really understand how the circuit will behave.
Okay. And why is that important?
Well, it's crucial for designing circuits that perform specific functions. Well, filters, for example.
Filters?
Yeah, they're used everywhere.
Okay.
From audio equipment to wireless communication systems.
So a filter can select certain frequencies and reject others.
Yep. It's like a gatekeeper for frequencies.
That's pretty amazing.
Yeah.
It's like the Bode plotter gives us a secret decoder ring for circuits.
Yeah, a way to understand their language.
Okay, one last question about the Bode plotter.
Sure.
Our sources mentioned that it needs an AC source to function.
Oh, yeah, that's important.
Why is that?
Well, remember, its whole purpose is to analyze how a circuit responds to AC signals.
Right.
So it needs that AC source to provide the test signals.
Okay, so it's like the Bode plotter is conducting an interview.
Huh. I like that.
Right, it's using those AC signals to ask the circuit.
Yeah, how do you handle these frequencies?
And the Bode plots are the circuit's answers.
Exactly. It's revealing its inner workings.
That's a great way to think about it.
Yeah, it's a really powerful tool.
Sounds like it. Well, this has been a fascinating deep dive.
It has, hasn't it?
We've gone from simple meters to complex oscilloscopes.
Yep, and everything in between.
And even this specialized Bode plotter.
A whole world of AC measurement.
It's incredible how much human ingenuity has gone into developing all of these tools.
It really is.
For measuring and understanding something we can't even see.
Alternating current.
It really is a testament to our curiosity.
It is.
And our drive to learn and explore.
And who knows what the future holds.
Right. What new tools and technologies will we develop?
There's always something new on the horizon.
That's the beauty of it.
Exactly.
Well, I think that's about it for our deep dive today.
Okay.
We hope you've enjoyed the journey.
Yeah, thanks for joining us.
And learned something new along the way. Thanks for listening.